Welcome to today's session. In today's session, we will discuss about pulse width modulation. In PWM, as we define, the width of the pulses will varies in proportion with the amplitude of the modulating signal. In the figure, it consists of a message signal, a continuous time signal, and a carrier signal which is nothing but a pulse. According to definition, you can observe the output waveform of PWM where the width of the pulse will be varied according to the instantaneous variation, amplitude variation of modulating signal. As the amplitude of modulating signal is high, the width variation is more. As the amplitude of modulating signal is minimum, the width variation is minimum. So that the definition is satisfied, and this is the waveform of PWM, pulse width modulation. According to input signal, here the width will be varied. Input amplitude message signal according to. Coming to PWM generation, a simple circuit we are observing here, which is consisting of a simple comparator and monostable multi-vibrator. For the comparator, we are applying two inputs. One is input signal, the other one is sawtooth generator. The sawtooth generator will generate a sawtooth signal of frequency fs, and this is applied to inverting terminal of comparator. And then the input x of t is applied to non-inverting terminal of comparator. Well, as we know that the comparator output remains high as long as instantaneous amplitude of x of t is higher than the sawtooth waveform. This gives the PWM output at the output of comparator, and the leading edges of PWM waveform coincide with the falling edges of ramp signal. Therefore, leading edges of PWM signal are always generated at fixed time intervals. We can observe here by this waveform. As we stated that we are applying to the comparator our input message signal and as well as sawtooth waveform. So as you observed, if the signal PWM pulse is generated for the negative half cycle of this particular sawtooth waveform, depending upon the input message signal, as the what we said earlier, where the comparator output remains high as long as instantaneous amplitude of x of t is higher than the sawtooth waveform. This is sawtooth waveform. Higher than the sawtooth waveform, if you observe, this is higher than the sawtooth waveform. Up to this, the pulse will be maintained high. Then when it reduces, here it will be 0. Then here it is negative waveform, so that here it is greater, so that it will be high. And then here it is sawtooth waveform is greater, so that 0. Then so depending upon this, we will be achieving our PWM waveform. So that output you can observe that here the width of the pulse is varied. So this statement is important. That's why we are giving to the comparator. By the comparator, we can achieve our output. Coming to detection of PWM. In the detection, we all know that detection or demodulation is the reverse process of modulation. The input for this reverse process of modulation is modulated signal, PWM signal. And here we are using ramp generator and synchronous pulse generator and a simple adder, clipper and as well as low pass filter, so that we can achieve our output. This particular thing we can understand by these waveforms. This is our input of demodulation process. Then these are the synchronized pulses, and this is the ramp signal which we are applying these two signals to the adder. So this is adder output. So addition of these two will be getting the output of adder. This is synchronous pulses and this is your ramp signal out, ramp generator out. So by adding these two, this is the adder output. So the waveform will be like this. And this output waveform is applied. So observe here, these two ramp generator will generate the ramp signal, synchronous pulse generator will generate the pulse. These two will be added and given to the adder, so that added and the output of adder is applied to the clipper. So clipping, what the clipper will do, the clipper will clips the unwanted waveform. So here we are clipping to this particular level, so that only this particular waveform will be occurred at the output of clip. So this is the clipper output. Then this is applied to the low pass filter. As we know that low pass filter will shapes our output, so that output, if you join this peak amplitude, it is looking like our input modulating signal, which is the output of our PWM demodulation technique. Okay. So low pass filter is used to recover the original modulating signal. Okay. So by these waveforms, by this particular figure, clearly we can understand the operation of receiver circuit, that is detection circuit of PWM. So this is about PWM, pulse width modulation, generation and detection techniques of PWM. Thank you for listening. We will discuss PPM in our next session. Thank you.